Our next objective is to state and check the random 10% large normal conditions to construct an interval for a population mean. So just like we had to check the conditions for confidence interval for a population proportion, we have to do the same thing here, but there's only one minor difference really. The random, we just have to make sure it came from the sample mean and the sample standard deviation came from a random sample, so it's a trustworthy sample. Then if they're sampling without replacement, which generally we are, we have to make sure the 10% condition is met. And this allows us to ensure that our formula for the standard deviation is approximately correct. The large normal sample is where we have a little bit difference when we're estimating a mean. For population proportions, you just check the large counts, 10 successes, 10 failures. For the large normal sample, we have to make sure the population is either a normal distribution, so they have to tell us the population is approximately normal, or if they don't tell us that, then we have to use the central limit theorem, where the sample size has to be greater than 30. If they don't tell us that, or if we have a sample that's less than 30, then the last thing we can do is we can actually look at a graph of the sample data to see if it looks approximately normal. So we can't use T procedures or calculate a confidence interval with a T distribution if the graph shows strong skewness or any outliers in the sample. So now we have three different ways that we can check the normal condition or the large sample condition. Let's look at three examples here together. So determine if the large normal condition is met in each of the following settings. To estimate the GPA of students at your school, you randomly select 50 students. Here is a histogram of their GPAs. So we have 50 students in the sample, done. The sample size is greater than 30. Doesn't matter about the population. It's greater than 30, so we know we can proceed with T procedures. Next problem, how much force does it take to pull wood apart? The stem plot shows the force in pounds required to pull a piece of Douglas fir apart for each of 20 randomly selected pieces. So first, is our sample size greater than 30? No, we only have 20 pieces of wood. So then next we have to say, do we know if the population is normal? They don't tell us anything about the population. So our last hope to try and get this condition to be met is the distribution of the sample approximately normal? And if you look at this distribution, you can tell most of the area is high and then it stretches out low. So this is strongly skewed to the left, which means we cannot proceed with T distributions because it has strong skewness. Again, no, the stem plot is skewed to the left, strongly skewed to the left, and it also has possible outliers down here, which is also a sign that we can't use, can't be strongly skewed or have any outliers. And the sample is less than 30, so we can't meet this large. We can't proceed with T procedures. Last example, suppose you want to estimate the mean SAT math score at a large high school. Here's a box plot of the SAT math scores for a random sample of 20 students at the school. So first, our sample size is not greater than 30, so we can't just immediately check this one off. So now we need to look and see, or we need to ask, did they tell us anything about the distribution of the population? In this case, they haven't. We don't know if it's normal. We don't know if it's skewed. So our last check is, do we see strong skewness or do we see any outliers in this distribution of the sample? Which I don't see any. It looks to me like there is a longer tail being stretched out this way, but this isn't strong skewness because the median is still right in the middle of the box plot. So even though our sample is less than 20, since there's no strong skew and there's no outliers in the distribution of the sample, then we can proceed with T procedures and make a T interval. And the reason we have this last, if the sample is skewed process, is because remember, samples take on characteristics of their population. So if this sample is strongly skewed left, that means our population is most likely going to be strongly skewed left. If this one is not strongly skewed, but it maybe has a little bit of signs of skewness, that means that our population distribution is most likely not strongly skewed as well.